Next speaker is Kyungwoo and Ellis Hoag from Compiler Group and Meta. We have two speakers for the same talk, and Kyungwoo is going to be the first part, and Ellis is going to take over the talk later.
All right. Hello. Hello, everyone. My name is Kyungwoo, working at Meta. I work with Ellis, Julián, and Sergey on this project. The topic is optimizing function layout for mobile applications. So I will cover the first part of talk, while Ellis will cover the remaining parts. Okay. So profile guide optimization, namely PGO, is one of the key compiler techniques to improve performance and size of applications. PGO uses the program's dynamic behavior to optimize, to generate optimized binary. It has been extensively studied on the server workload by improving the CPU and cache utilization during the steady state of program execution. However, mobile apps are mainly optimized for size, which poses distinctive challenges when applying PGO. Mobile apps are largely I/O-bound due to frequent interactions with users. Therefore, the steady-state performance is not well defined. So in this presentation, I will focus on function layout in the context of two key objectives: app launch time and app size. Let's talk about app launch time first. A fast app launch leaves a good impression on users, helping in user retention, thus boosting our revenue. This startup performance is mainly influenced by memory page fault because app binaries are loaded to memory from disk for the first time. In a large commercial app, there are many use cases, even in startup scenario. So achieving a single function layout that are optimal for all use cases is a challenging task. Let me show a simple example with two traces. Here, red function represents executed function, namely hot functions. Ultimately, we would like to place these hot functions in the beginning of a binary so that we can minimize the memory page fault overall. So now let's move on to the next objective. The mobile app compress size is critical because mobile apps are distributed in a compressed form. This compressed size directly impacts the app download speed and also network bandwidth. More importantly, the mobile app platform may impose a size limit or may require user permission to download a large app. So the key idea for function layout in the context of app size is to co-locate similar functions. So here, similar function means some byte encodings are in common between two functions in their functions body. So for instance, in this example, same pattern functions like function 1 and function 3 are similar. So if we place these similar functions close to each other, then compression algorithm can place the same byte sequence by a pointer, thus improving overall compression. So here is our contributions. We proposed a first unified function layout based on bipartition, balanced graph partition for the two important key objectives that are seemingly different. First, we apply BP for the startup optimization with hot functions. Second, we apply BP for compression with cold functions. we evaluate our approach with a real-world mobile app developed by our company. We improve startup performance by 4% over the previous auto average approach. We also improved compressions by 1% compared to previous greedy approach, while it is much more efficient. Last but not least, through extensive reviews, we've already upstreamed the most of our code in LLVM. It's actually also part of our ongoing effort on a lightweight IRPGO that tries to minimize the instrumented binary overhead. So let's look at the compression problem first, PPC. Let's say we have 4 functions like this. We can compute a set of stable hash that represent each function. So basically, we compute hash for each instructions. For simplicity in this diagram, I just name U through U4. We can come up with a bipartite graph consisting of utilities upper end, or also functions on the bottom side. We connect between utilities and functions using edges, like this. Then our primary goal is actually to place functions that share utilities close to each other so that similar functions can be nearby, thus improving overall compressions. So our approach is based on recursive bipartition, basically. So given unordered functions, we would like to come up with some final order. Basically, we partition functions into 2 groups, left and right, while improving certain objectives that we set. Likewise, for each group, we continue partitioning functions into 2 groups recursively. The final order of functions are simply concatenation of them. Note, these operations are completely independent, so we can run in parallel. Now, key question remains, how do we going to bisect functions? So given this bipartite graph, if you see the orange utility like this, all the edges go to the left group, which is good as the function sharing the utilities are close by in the same group. On the other hand, if you see the purple utility, the edges actually reaches 2 different groups, which is not good. So basically, intuitively, our goal is to try to maximize the orange utility possible while minimizing the purple utilities. So to formalize our objective, for given utility, let's count edges to each group, X and Y respectively. Then, there are many ways to define it. We are interested in the total, all the utilities. So the combined cost is like this. There are many ways to define a cost functions, but we use uniform low gap functions inspired by graph compressions. Intuitively, if either only X or Y becomes large, like the orange utility functions, the cost will be low as a negative value. So now our goal is to minimize this cost value by exchanging functions to different groups. So for more details, please refer to the paper. So let me give you a more concrete example. So same example, start with I've already shown earlier. Now, each function represented as a set of unique hashes. And then we have this bipartite graph originally. So now let's partition into 2 groups, left and right. And then if you just count the number of edges for each utility, it looks like this. And then overall cost is going to be some negative value, 3.7. Now PPC actually tried to exchange a function F2 and F3. Then, if you compute the edge count for each utility, if you see U2 and U4, they are all L or R value only. So the overall cost will be even lower. The mapping to startup performance cases, please refer to paper or you can talk offline. Now, pass it to the Ellis.
Hi, thank you. So my name is Ellis, and I'll be going over some of the implementation and evaluation details. The balanced partitioning algorithm has been partially upstreamed to LLVM. Now, I say partially because it's currently only used to reduce page faults, but we do plan to add more patches to use balanced partitioning to improve compressed size as well. The algorithm is very fast. In one of our largest scenarios, we order 1 million functions in about 20 seconds, which is more than fast enough for us. And the speed up comes from a few things. First, each bisect step can be run independently, so we run them on different threads. And since our cost function uses logs, we can pre-compute a 64 kilobyte log table, which is small enough to fit in the cache, and that gives us more speed up. Another interesting note is that throughout the algorithm, when we decide to move a function between buckets, there is a small chance that we don't move it. And this actually does improve the quality of our function order. Our algorithm makes heavy use of instrumentation, so I'd like to talk about it. The instrumentation we collect uses function traces from mobile devices. What are function traces? They're just an ordered list of executed functions. Offline, we combine traces into an indexed profile, and this is the profile that we'll feed into the compiler. We sometimes get thousands of traces, but we found that around 300 is good enough for good results. So we use reservoir sampling to merge a stream of traces into an indexed profile. This instrumentation has also been upstreamed to LLVM's IRPGO, and you can see this link for details. I should also mention that this upstream instrumentation is slightly different from the one we used in our evaluation, which unfortunately is closed source, which is why we are excited to have upstreamed this work. The pipeline to collect profiles is also interesting. We start by building an instrumented build from our source code. Then we install and run this build on many mobile devices. Ideally, these devices run the app under normal conditions that are representative of our user population. As the app runs, it will dump and upload raw profiles to our servers. Then we can download these raw profiles and merge them into a single index profile that will be fed into the compiler. We use lightweight instrumentation, which means the instrumented binary has low performance overhead and small size overhead. This also means we need access to the instrumented build while we are creating our indexed profiles. Finally, this index profile is used to create an optimized build, or the PGO build. During optimization, we actually run balanced partitioning twice. The first time is during post-processing, before we optimize the binary. We take the traces from the profile and give it to the algorithm to find a function order to improve startup. Then, during link time optimization, just after code gen, we have access to functions machine code, and so we run balanced partitioning a second time on cold functions to improve compressed size. We concatenate these two function orders and pass them to the linker to lay out functions in the binary. We are actively working on trying to run balanced partitioning only once on a shared objective to improve both startup and compression, and this will likely happen just before linking. For evaluation, we show the total compressed size improvements on 3 apps: social app, chat app, which are iOS apps, and also Android native, which of course is an Android app with native code. The algorithm called Greedy in light blue is the prior algorithm, and BPC in dark blue is ours. You can clearly see that BPC has a larger compressed size improvement across all 3 apps. Now, you might think that an improvement just under 2% might not be significant, but these apps are installed on billions of devices, so this really does have a real-world impact. Here we show the compressed size improvement of just the text section of the binary. Remember that we are only changing the function order, but these apps contain much more than just functions. They have data sections and images and other resources. So this graph more accurately represents our algorithm's contribution to the size improvement. Lastly, we use major page faults as a proxy for app cold start performance. The fewer pages that need to be loaded, the faster your app will start up. We've measured the average number of page faults in production for 2 of our iOS apps. For one release, we used the prior order average algorithm to order functions, and then in the very next release, we shipped with our new BPS algorithm. Unfortunately, there were other differences between these 2 app releases because our teams are always shipping and maintaining new features. So we ran this experiment a few times to confirm that the performance win was real. And as you can see, balanced partitioning does reduce the average number of page faults. And to conclude, we have described the balanced graph partitioning algorithm and showed that it improves real-world mobile applications. It reduces cold startup time by 4% and reduces compressed app size by 1%. The runtime of the algorithm is negligible with respect to the whole build pipeline, and it has been upstreamed to LLVM, so you're free to try it out yourself. And thank you so much for listening.
All right, it's Q&A time. Yes, please.
It's kind of interesting approach, but the question remains is why you just kind of make the balance in each level is always better. Such as think about the quicksort. Even though you might have each level of the recursion, in some cases you have a biased numbers of elements in each node, right? Let's say you just do the quicksort. Maybe at one point, the left-hand side has a larger elements than the left-hand side, right-hand side. But overall, at some level, at each level, achieve some better performance that gear toward the shortened depth of the recursion height. You understand what I'm asking? The thing
The
is,
question is about why, so whether the balanced graph partitioning is going to be optimal or not.
that's right. So you
Yeah.
focus on one level
So
by level.
basically, this is kind of non-trivial problem to solve optimally. We can actually, the greedy approach is more close to what you actually described.
That's right.
We actually try to place functions one at a time that are match the previous function that are already placed. So basically, counting number of stable hash that are matched just right before the previous function that already laid, one by one. That's actually a greedy approach. But as you see the graph, I mean the comparisons, the initial approach that we took, greedy actually is worse than the one that we apply with the balanced partitioning graph. And also, more importantly, this is production environment. The build time is something that we cannot ignore. So if you just greedy approach, it took many minutes, like 40 minutes for the large million functions. But in this approach, it's just within 1 minute. So we have to solve these 2 things. We don't think that the balanced approach is not optimal, but it's going to be actually even better performing in terms of precision and also in terms of build time.
Thank you. One more question. And what does it mean by the partially upstream to the LLVM? So what's that supposed to mean?
Okay.
So like I said, a lot of the code we used is kind of closed source, but we are working to upstream pieces of it to LLVM, so it's useful. And specifically, I said partially because we can only use balance, like the work I upstreamed only is used for cold startup improvement.
So LLVM is an umbrella of many different modules, and where your VPC is actually fitted into the LLVM. Is it linker or where?
Yeah, so in this slide, we kind of run BPC just before linking using custom code.
Thank you for the questions. And I have one question. Oh, do you have any? Yes.
So you talked about the improvement like relative terms. Do you have the absolute numbers? How many seconds or milliseconds faster you start up, or the code size? How many megabytes smaller it is?
So once again, even for startup cases, we have many traces that represent many user scenario, right? So if you just come up with a single function layout, they cannot be optimal for either traces. We try to minimize page fault overall. So basically, we have some metric to minimize the average page fault. So if, let's say, we have two over third function and traces from the two over my preparation, there's a user cases a lot. Then we actually try to optimize those majority of populations. Basically, make majority of people use happy. So there cannot be a single layout that can be optimal for all, that meet all use cases, for sure.
But the question is, so how much faster the startup is, but not in the percentage time, but in the absolute time of,
Oh, in terms of time, it could be translate less than 100 milliseconds-ish. Yeah, that's, just rule of thumb number. Yeah.
Thank you.
Yeah.
So as far as I understand, this is only done on the functions that are already written inside of the source code, right? So there's this project Bolt, which dissects the basic blocks of a function into separate parts and then reorders them. Has this been evaluated on the post-Bolt step to reorder basic blocks to even increase that more, like the performance benefits and the compression size?
That's actually good questions. I mean, actually, Bolt is one of my neighbor teams working on, so in the same company, same team. This is a neighbor team. So Bolt hasn't, as far as I understand, Bolt is fully enabled for ELF, but not the Mako. There was some certain limitation in terms of the object, the way to representing the extra profile data in the object layout. So anyhow, so basically in the Mako environment that we are mainly targeting, so splitting block within the function is technically challenging. So that's the primary reason. But we would like to evaluate actually if we can come up with the solutions that can carve out block out of functions to see if we can improve better in terms of performance and compressions. But that's something we have to consider for the future.
I mean, yeah, obviously there is a trade-off between how many blocks do I want to reorder. Like if I have like 5 instructions per block, it takes ages to sort them perfectly. And if I have just 2 blocks, then I don't gain as much.
Yeah, and also there was a certain thing you have to keep in mind is that we are targeting mainly the mobile apps, especially iOS app, where the function size is pretty small. It has only 2 or 3 functions, and there are a lot of cores within the functions. So even though we have come up with a solution that can, place different blocks across functions, but probably we might not see much improvement. So this is a little bit target. Bolt is mainly target for the server application where functions are large, aligning happens a lot. Then carving out block makes sense, but here blocks are already very small within the function. So
Okay, thank you.
okay.
Yeah, this will be the last question for this talk. If you have any more questions, please discuss offline.
Thank you. It seems to me that reducing the size and improving the locality of functions is kind of in conflict. I'm not sure whether you mentioned that at all, and if you did, why is that not a problem? So you have 2 objectives when reshuffling your functions, right? You want to compress, you want to improve the compressibility of your text segment, and you want to improve the locality of functions that are used at the same time. Is that a conflict?
Are you asking? Can you clarify the problem?
You are optimizing the order of functions, right?
Yes.
So that's one thing, and you have 2 objectives in doing so.
Yeah.
You want to reduce you want to improve the compressibility, and you want to improve the locality
Of the
code.
Functions. Yes.
Is that are those 2 objectives in conflict?
No,
Would you like
there's
to answer?
no real theoretical reason why we can't use like a shared objective to optimize both. But in our implementation, as it stands, we do them separately for implementation details. But we would like to order them all at once during link time.
Yeah.
Okay. Thank you.
All right, let's give another applause to the speaker.